Hi everyone, very pleased to be part of this first edition of the Neuromatch conference. I'm going to present a project that is entitled Learning a Categorization Task through Confidence Control Hebbian Learning. This is a project that I have done during my PhD under the supervision of Jean-Pierre Nadal at ENS in Paris. So first a bit of introduction about the models that I considered. So the goal of this project was to study the learning of a categorization task by a neural network. And the neural network is composed of two layers. The first one, the bottom one, is an encoding layer composed of tuning curve neurons. And this layer receives a stimulus and encode it and sends the information to a decision layer. And this decision layer is composed of a winner-take-all attractor network, where after competition, it will give a category membership for the stimulus that has been presented. So the coding layer can be, like the encoding chosen for the coding layer can be different depending on what we want to study. For example, it could be a uniform coding, so in red here, where every neuron in this layer has the same tuning curve with the same weights and uniformly spaced along the stimulus axis. On the opposite, because the goal of the network is to perform a categorization task, this coding layer will be optimized with respect to this categorization task, and this will lead to tuning curves that are dense towards the boundary of the category, 0.5 here, meaning that the network will allocate more resources to encode hard stimuli and will have less neurons coding for the stimuli far from the category boundary. Because during this project, I was interested in the learning of this categorization task, and so I considered three possible learning rules. The first two are like standard in the field and correspond to the pure Hebbian reinforcement learning rule and the reward modulated Hebbian learning rule. So in those rules, the synaptic modification depends on the learning rate delta, the pre and post synaptic firing rate, Rj, Ri, and here the reward R, and in the case of the reward modulated rule, reward minus the mean reward that has been obtained upon presentation of stimulus X. I have designed a third learning rule specifically for this project, which is a confidence control reward-based Hebbian learning rule, where the synaptic modification is the following. It is subject to pre and post synaptic firing rate and the reward R. However, the learning rate delta is going to be modulated by the confidence in the network, with Q being 0 if the trial is a high confidence trial and 1 if the trial is a low confidence trial. And by confidence in the network, I mean the difference of activity between the winning and the losing population at the time of the decision, meaning that high difference between those activity will correspond to a high confidence trial, and a low difference between those population will correspond to a low confidence trial. So now, if we look at the different type of encoding of the coding layer and those three learning rules, we find the following heat map of performances, where those heat map are color coded, and the color represents the sign of the difference of performance between the task optimized and the uniform coding layer. Meaning that if it's red, it means that after learning, the task optimized coding layer performs better than the uniform coding layer. If it's blue, it means that it is the opposite and the uniform coding layer performs better than the task optimized one. On the bottom line on this figure, you have the Hebbian and the reward modulated Hebbian learning rule, and you can see that surprisingly, there is a huge region of parameters for which the uniform coding layer performs better after learning than the task optimized one. And that means that the network is not able to make use of the fact that the coding layer has been optimized, and having this coding layer optimized leads to worse performance than just having a simple uniform coding layer. However, in the case of the confidence control Hebbian learning rule, it's not the case because at most, performance between task optimized and uniform coding layer are the same. And there is a big region of parameters for which it is the opposite. It's red, meaning that the performance of the task optimized network are better than the one of the uniform coding layer. And that means that with this confidence control learning rule, the network is able to make use of the fact that the coding layer has been optimized and can allocate more resources to have better performance. So in summary, so this project has shown that neural coding and learning algorithm cannot be considered separately because having optimized neural coding doesn't always lead to better performances if the learning algorithm is not able to make use of it. Moreover, and there is more details in the paper of what are the reasons was the fact that the confidence control learning rule gives better performance than the other learning rule. One of them is that shown that this confidence modulation of the learning rate approximates gradient descent during the running of a categorization task. The last point I would like to make is that this confidence control learning rule doesn't require the network to keep in memory the rewards of the previous trials, and does so by just having an internal variable that is a difference between neural population. And this internal variable is going to modulate the learning rate and allow the network to learn efficiently the categorization task without having to keep in memory all the previous rewards. With that, I would thank you, and I am available on Discord and Twitter during the conference to answer any question you could have.